Okay, so we are going to start today with chapter 7. We finished chapter 6. Sorry. Yeah, we did finish chapter 6 last time, talking about valence bond theory. So we went over Lewis's theory, valence bond theory, molecular orbital theory. And remember, in those three theories, we're talking about bonding, and especially with the last two, valence bond theory, molecular orbital theory, we're focusing on bonding that involves sharing of electrons, so covalent bonds. Okay, now that we're done with that, we're going to move on to chapter 7. Chapter 7 deals with traditional chemistry. So now we're back to, okay, I see it's working. Okay. Sorry, I was trying to help a student access a video. Something had happened with the video, so that's where I was on a different screen. But anyway, okay. So we're back to traditional chemistry. We're dealing with physical changes in matter. So we're now ready to finally talk about chemical reactions. But before we get into chemical reactions, we have to make sure that when we are in the lab, the observation we're making is really due to a chemical change, not a physical change. So before we get into that, we want to review what a physical change is versus a chemical change. So we start here with physical changes in matter. What exactly is a physical change? When you're in the lab, sometimes the physical changes will have physical observations, right? You'll be in the lab and you see something transforming in the chemical. And with the physical change and the chemical change, both will have some kind of visual evidence of either, right? So when we're looking at physical changes, what we are seeing is only the appearance or state is altering. So the appearance of the chemical will look different, but the composition is still the same. The example they have given us here, by the way, notice that we have two levels of observation in this image here. You have the macro level, and the macro level is usually what you will see in the lab, and then you have the particulate level. Particulate level is a level right here where they're showing you molecules, right? The fundamental level, the building block level. So macro is what we see with our eyes. Particulate is what energetically that explains what we're seeing with our eyes. Observation here is you're in the lab and you're boiling water. This could probably even be at home because this looks like a regular stove, right? Anyway, water is being boiled, and then the liquid water to water vapor here to a vapor state here, or steam or gas. So you can say vapor or gas state. So what is actually happening? What they're saying here is even though we're seeing a physical change, right? We are observing a change in the appearance. If you analyze the liquid water and you take a sample of the gas and analyze it, what you will observe is fundamentally we're dealing with the same chemical, but the only difference that causes a difference in its appearance is how far they are spaced. So here we're seeing a physical change where in the liquid state, the water molecules are very close to each other, therefore affecting each other. I'm trying to make sure I don't go to Chem 1412 because I'm teaching 1412 and I'm teaching 1411, and the concepts sometimes overlap. But anyway, we're looking at a physical change. So in the physical change, at the particular level, the biggest thing that changes is the spacing of the molecules. And there's intermolecular forces too, but the spacing of the molecules. So some are very close together and some are far apart. Okay. In the gas state, the water molecules are far apart, but they're both still water molecules. You got H2O up here, H2O up here. The actual chemical, the composition of the chemical has not changed. So we're told here, atoms or molecules that compose a substance do not change their chemical identity during a physical change. So the chemical itself does not change, just the spacing changes. When water boils, it changes from a liquid state to a gas state. The gas remains composed of water molecules. So this is just a physical change. I mean, I'm adding the word just to emphasize that just because you're seeing a difference doesn't make it a chemical reaction. Okay, well, we are seeing a difference here too. Actually, they didn't show us the beginning, but let's pretend this small part of the nail is what the whole nail looked like before. So this is be our before, and this bottom part here will be our after. Okay, so what is the chemical change? We're told once again, you will physically see something different. The appearance will change. But not only will the appearance change, so will the composition this time. The chemical composition changes. They're showing you changes that alter the composition. They mean here chemical. The chemical part is implied. Chemical composition of matter is classified as a chemical change. During the chemical change, atoms will rearrange themselves, transforming the original substance into a brand new substance or a different substance. Okay, so you have atoms rearranging themselves, and they rearrange themselves differently. It's not just a rearrangement, bonds will break, new bonds may form, right? Sometimes a new element or atom adds to the pre-existing element, and in the end you have a whole new chemical, right? Example here is rusting of the nail. So you have a brand new nail that is not coated with a protectant. And if that happens, as time goes by, you have moisture from the atmosphere, you have oxygen, and the nail that just used to be iron reacts with the oxygen from the atmosphere with the help of moisture, and now it forms iron 3 oxide. Iron 3 oxide is the chemical name of rust. You have your shiny new bike, and something happens to where you chip a part of the protective cover on the metal on your bike. Same thing happens. You have a nice new car, and then maybe part of the car, the protective layer on the car, is chipped or is scraped off. Rust happens. You have metal and it's around long enough, rust happens. Okay, so this happens naturally. So here is the iron atoms by themselves, and then once oxygen gets incorporated, you see the bonding is different, right? Over here in the beginning you have it looks like what, 8, yeah, it looks like 8 iron atoms bonded together with one in the middle, right? 1, 2, 3, 4, 5, 6, 7, 8 with one in the middle. So you got 9 atoms of iron combined together when it's just iron element by itself, the iron atoms. And then when the oxygen comes to incorporate itself within the structure, now the oxygen is literally part of the equation. And you can see right here, the bonding changed completely. The bonding style changed, right? Now iron is surrounded by oxygen versus back here, iron was surrounded by iron. Okay. So we're told here rust occurs when iron atoms exchange electrons with oxygen atoms, combining to form a new or different chemical substance. Iron rust is composed of iron 3 oxide, which is this right here. The appearance of iron rust is, it looks more like dirt, but it's really just rust. Okay, so we're going to do a practice problem, conceptual connection. Chemical change. Which change is a chemical change? We are told here evaporation of rubbing alcohol, burning of a lamp oil, forming frost on a cold night. So while we're looking at this, I want to look at natural occurrences or events that happen in our lives that are listed under chemical versus physical changes. So I'll start with physical. These are considered physical changes because even though the appearance changes, they're still physical. Okay. Number one, let's see. So I'll say here, whole paper ripped to shreds. Okay. This example I'm giving here is a physical change because when you have a whole piece of paper and then you rip the piece of paper to shreds, the appearance looks different, right? The whole one is one single paper. The one that's ripped to shreds is tiny pieces, but it's still fundamentally paper. So that's an example of physical change. But what changed here, as we can see, let me write it here, change in size. So when the change in the size of a particle or an object occurs, it is still physical change. Okay. Number two, if you have a change in state. So change in state, example, liquid to solid, liquid to gas, solid to gas, all these, okay? These are all change in state. So let me go ahead and write it better. Liquid to solid, solid to gas, solid to liquid, and vice versa. All of these are part of physical changes, right? Fundamentally, the chemical is still the same. So forming frost is going from a gas to a solid. So that will be physical change. C is physical change. They're asking you which one is a chemical change. Evaporation. Oh, I should have. Okay. Well, I'm on number two. Let me explain that part. So if you go from gas to solid, this is usually called not condensation, but oh, no, I forgot the term. Forming frost is the common term. Gas to solid, solid to gas is usually called sublimation. Sublimation. So be aware of the thermodynamic terms. Gas to solid, solid to gas. These are all called sublimation. And then gas to liquid is called condensation. Liquid to gas, evaporation. What else? Oh, liquid to solid. The common term is freezing. The thermodynamic term is fusion. Okay, so when I'm writing all this down just to say, be aware of thermodynamic terms. Like if they say a fusion happened, don't panic. They're just talking about liquid becoming a solid or solid becoming a liquid in that state. That is a thermodynamic term. So thermodynamics is the part, it's a subsection in chemistry where they deal with stability and spontaneous reactions. So it's a group of chemists that specialize in spontaneous reactions and stabilities of molecules. Okay, so because it's a subgroup of chemists, they tend to have their own terminology to describe what we are commonly familiar with. So this would be under sublimation, condensation, evaporation. Evaporation also goes with vaporization. So just in case you're reviewing this in the textbook or online and you see these terms, just understand this is what that group of people, call these transformations. Okay. Then, of course, when it comes to the chemical change here, I've written all over here. With the chemical change, you want to be aware of rusting. Rusting is a chemical change. So right here, chemical change. I'm running out of room. Rusting, we've seen that, an example of that. Boiling or cooking. These are all examples of transformations that we are very familiar with that fall under chemical change. Rusting, boiling, cooking. Okay? So based on that, or even I guess if you're boiling and cooking, you're also burning, right? Burning. These are all. And they can use the term combustion also. Combustion is another term by the thermodynamic people that is talking about burning. Okay, so once again, just be familiar with these terms. And so if we have burning here, this would be the chemical change. Physical, chemical, physical. Okay. Okay, so moving on. Now we're looking at this question. Now we have titles here, so it kind of gives you a clue into what we're looking at here. The diagram on the right, this diagram right here, represents liquid water molecules in the pan. Which of the three diagrams below represents the water molecules after they have been, remember I told you about those terms, vaporized. Vaporized was under liquid to gas. They're already using the thermodynamic term, vaporized. Okay. Vaporized just means it's been boiled. So you've gone from liquid. We're looking for gas, water. Okay. First of all, we have to find the water molecules and then find out which one looks like a gas. These are not water molecules at all. These are oxygen and hydrogen separated. This looks like oxygen molecule and hydrogen molecule. So we got oxygen molecule right here, hydrogen molecule right here. Once again, not water. Here you got the hydrogen and the oxygen atoms actually separated. So here you got oxygen atom, hydrogen atoms. So if you're comparing the liquid to A, this will actually be a chemical change because the connections, the connectivity is completely different. If you're comparing the liquid to B, that will also be a chemical change because the connectivity or the connection has changed completely. But if you compare the liquid to A, that is a physical change because in this case here, as you can see, the connectivity hasn't changed. The only thing that has changed is the spacing, therefore making A the gas state of the picture on the right. Okay, so please notice that both this and this are chemical changes. I'm going to write here. Oh, no. Why am I writing with a marker? Chemical, physical. Okay, I need that to be yellow. Okay, so chemical, physical. Okay, now we're getting to balancing equations. We're looking at this and we're saying you want to know how to write and balance a chemical equation. When we examine chemical equations, what we see is, for the most part, in general, your reactants are on the left and your products are on the right. The reactants and the products are separated by arrow. Give me just a second. Let me grab some water. The reactants are on the left, the products on the right. So the yield arrow, this is the yield arrow, separates the reactants from the products. So for the most part, the reactants are considered the beginning of the reaction, and then the products are considered the end of the reaction. So we read from left to right. Okay, once again over here, notice you have two reactants, both at gas state, and then you have two products, one is gas, one is liquid. What are we communicating in the chemical reaction? In a chemical reaction, we're giving the viewer, the reader, the bottom line. We're telling them kind of like a roll call. What chemicals will react? What will their products be? Okay? And then what is their physical state? So we're told here, we're given the person that's reading the chemical identity of the substances in the reaction, the reactants and the products. And then we're talking about their physical state also. This is a gas, and these two are gas and liquid. Okay. In a way, we are also talking about how much of each is reacting, but we haven't gotten to that part yet. They're trying to unfold the mystery a little at a time. So here, G in parentheses means that chemical has to be in the gas state. So if you're trying to plan a reaction and you get the balanced equation, you have an idea, oh, I need this chemical in the gas state. This is liquid. So when they say G for gas, liquids, these are all pure forms of the chemical. So gas is a pure form. Liquid is also a pure form. And then solid is also a pure form. Okay, so the purity is implied. When they say solid sodium, they mean just sodium, nothing else. Now, once they say aqueous, aqueous is usually a mixture. Okay, aqueous is normally a mixture of ionic compound and water. Okay, So gas is pure, liquid is pure, solid is pure, and then you have aqueous. Because I've had students in the past, in the face-to-face class, you know, from very good schools, four-year colleges, and then they're asking me, what is the difference between liquid and aqueous? Now, that's a very good question. When you're in the lab, depending on what kind of aqueous mixture you have, the liquid, like liquid water, looks just like salt water. So if you have water in a liquid state versus salt water, so if you get clean salt, not dirty salt, you have to get clean salt. So salt water, so let's say salt from the lab, that usually tends to be very pure and clean. You have salt water. You can probably, if the salt is not very clean, you might tell a difference because the salt water looks a little murky, right? But let's say you have sugar water. Sugar water, I would say this tends to look pretty clear to where if somebody secretly mixed sugar into water and had a glass of sugar water sitting next to just regular water, if you walked in there and neither was labeled, it will be difficult for you to tell one from the other. So physically they look the same, right? But when you test them, the sugar water will be different because it will have two compounds versus the liquid water will be just the pure liquid. Okay. And then they finally say it. In the balanced equation, not only do they give you what the chemicals are, what the physical state should be, they finally tell you here they give you the relative amounts of products and reactants. When they say relative, I have to say this here. This term relative is very, very important. It should have been in a different color. It's relative, it's all relative. And what relative means is this if and then statement. Okay. So back here, is this equation balanced? Yeah, it's balanced. So this balanced equation gives us the relative amounts of the reactant required. So I will focus only on the reactants right now because I don't really have a lot of writing space. If, since there is no number before the formula, the 1 is implied. This one here has a 2, so the 2 is not implied, it's actually stated clearly. So if one amount, and I'll keep it generic, one amount of CH4 is used or reacted, two amounts of O2 are also reacted. Okay, the balanced equation. So here's the thing. I don't think we haven't talked about the scientific process, right? But we have been doing it this whole time. The scientific process is this. It's a step-by-step process that begins with a judgment, right? It begins with judgment. Now, in the world outside of science, it's not very good to judge people or situations, right? Like, don't judge me. In the world of science, everything starts with judgment, especially the scientific process. It starts with a judgment. Well, actually, technically, after an observation. So you have to observe something and then make a judgment. So when you observe something and then you make a judgment, then you have to, the judgment that you make has to be an educated judgment, not just like a wild guess judgment. It has to be educated. That means it's based on something that you know for sure, some kind of experiment and experience or something, right? And that judgment is called a hypothesis. And then you go to the lab to test your hypothesis. You don't make a judgment and then walk away and like, hey, I've spoken it, it's been said, I'm moving on. No, you have to test your hypotheses and you perform a series of tests of these hypotheses. And then if each time your hypothesis is proven true, then your hypothesis, I use the term graduates because it's not in the phase of being tested anymore, but it graduates to become a theory. It takes a lot for something to become a theory. It has to be tested back and forth and back and forth and back and forth, and it has to be tested by many people. And then when everybody gets the same conclusion, then your hypothesis, kind of like after 4 years of school, graduates and becomes a theory. And we do that because when something becomes a theory becomes something that people fall back on to make new observations and new decisions. So you want to make sure a theory is tested. So I say that to bring this forth. When we look at the balanced equation gives us something to hold on to. Okay. It tells us when you go to the lab to react these two molecules. So the balanced equation is kind of at that theoretical level. It's been tested before and proven, right? So when you go to the lab and you're trying to react these two chemicals, you should expect every one amount. Now the amount can be in moles. So if the amount is in moles, you can say every 1 mole of CH4. If you're going to react that, you should expect 2 moles of oxygen to react with it. Okay? So after somebody did this experiment over and over and over again and proved it, now you are launching off of their proof. And this is a balanced equation. Okay? So you want to make sure when you're balancing the equation, you do a lot of work, you test it out and everything. Okay. So they're showing you the balanced equation. The amount of every substance used and made in the chemical reaction is related to the amount of all the other substances in the reaction. This is called the law of conservation of mass. So in the law of conservation of mass, which is not stated very clearly here, the bottom line is this: mass of reactants. Ooh, if I can spell reactants this morning, reactants equal mass of products. Okay, so the reactants are the ones on the left, right? So this when the equation is balanced, it works out so that if you take the atomic mass, they're talking about the atomic mass here, atomic mass, and even the weighed mass, just mass in general, any kind of mass. When you calculate the mass of the reactants, they will equal the mass of the products. Okay, even in the case when a gas is being produced. So you only get to this point after you've balanced the equation. When we start to relate the amount of substances in the balanced equation, this is called stoichiometry. So they say the study of the numerical relationship between the chemical quantities in the chemical reaction is called stoichiometry. When you start relating the amounts, the numerical amounts of either the reactants or reactants and products, this is called stoichiometry. So we're going to go straight into balancing the equation. Right now, we're learning balancing. Later on, we will learn how to complete the equation. Okay, so first one that we're given over here is this formula here. Let me copy it, move to a new page, and then we're going to balance it. Now, when I was in school, in the curriculum that we had, so we used the GCSE curriculum, which is the British curriculum. That's usually the common curriculum used in most African countries, like for the basic school, unless it's a American-based school. Then if it's an American-based school, they use the American curriculum. We were doing balancing equation in middle school, and my teacher introduced the, what is it called? Balance by observation. I hated that. I hated that method because you could get it right or you could get it wrong. I don't like investing in things that I get. I know it's not a very mature outlook on life, right? I just don't like failing. I don't like investing in something just to come out of it and I'm like, well, you have an equal chance of getting it right or getting it wrong. I'm like, can you teach me just the right way? If I'm going to invest time doing this, can I just get it right? So my teachers taught me that whole by observation. And just like they taught me, they got it wrong sometimes, they got it right sometimes. I mean, when they got it wrong, they used a different method to eventually get it right. I didn't like that. So as a teacher, I came up with a more accounting method that helps you get it right more than you get it wrong. What we're going to do here is list the elements below the compound, right? For example, I'm starting here with cobalt and oxygen. Here I have carbon, and I'm going to list the elements, right? And we're going to try to use law of mass action to balance the elements on either side, which will then balance the compound or balance the whole equation, sorry. CO, C, O. Okay, so I'm going through and I'm trying to figure out how many atoms do I begin with, and then from here I'm going to balance this out. In the formula right now, I have 2 cobalts, so I put 2 here. I have 3 oxygens, so I put 3 here. I have 1 carbon, I put 1 there. In this formula up here, I have 1 cobalt, I have 1 carbon, I have 2 oxygens, right? So I'm writing the formulas below it. Sorry, I'm writing the atoms or the elements below the formula, right? Okay. Now, when it comes to balancing, at, at some points I am going to examine. Let me make sure I have one cobalt on the left, one on the right. So when I'm saying one on the left and one on the right, I mean only one formula has cobalt on the left and only one formula has cobalt on the right. Same thing with carbon and oxygen. So it doesn't matter which one I balance first, it should theoretically work out. Let me try balancing cobalt first, okay? If my goal is to balance cobalt, the only way I can balance is by multiplying. I cannot add numbers to balance. I can only multiply the existing numbers by whatever number I want. I can use whole numbers or fractions, but I'm going to stick with easy numbers and stick with whole numbers. So I'm trying to make the left cobalt match the right cobalt. I'll multiply the right number by 2 to get 2 cobalts on the right. So right now, the cobalt on the right is balanced. That's what it looks like to me, right? Let me see. And then when I look at the carbons look balanced too. Now, the next thing I do is try to balance the oxygen. So I just realized I did something similar to what my teachers did after I criticized them, right? Which is, I'm a little rusty on balancing the equation. It's been a whole semester. Okay, the oxygens we're trying to balance this, but we have an even odd situation, right? So we cannot make the right equal to the one on the left or vice versa, but we can make them both equal to the greatest common factor, which will be 6. So to do so, I want to multiply the left one by 2 and then the right one by 3. You see that? So you could have started with that one first if you want to do it one time and do it well, which is deal with the even odd situation. If you have an even number on the right and odd on the left, that could work. If you do that here, you end up with 6 oxygen on the left and 6 on the right. Okay, but since when we are done, we're going to be putting this multiplier before the formula, which will apply to all the atoms in that formula or in the compound. Whatever you do to the oxygen, you have to do to the carbon. So since I multiply the oxygen by 3, I have to multiply the carbon also by 3 to give me 3 here. Okay, I only want to put this number in up here when I know for sure I'm done. So right now I have 6 oxygen, 3 carbons, and then I have 6 oxygen on the left, but I have 1 carbon. To multiply the carbon by 3 to make this 3, and then right here, let's see. I need to multiply, since the cobalt and the oxygen are the same formula, I need to multiply this cobalt by 2 because the multipliers have to be the same if the elements are in the same compound, right? So now the cobalt has changed to 4. So I'm going to take this and change this to 4 so everything matches. Okay. Okay. So once again, part of the reason why I'm showing you this method, well, my teacher, they would just write a number here, write a number here, write a number here, erase it, write a number here, here, here. And I'm like, whoa, what is this? So yeah, even though I had to make some adjustments here, it's still a little bit more stable than what they were showing me. Okay, let me check. Quick check. Cobalt 4 on the left, cobalt 4 on the right, carbon 3 on the left, carbon 3 on the right, oxygen 6 on the left, oxygen 6 on the right. Okay, since my number of atoms match on either side, I now will take the multipliers that I used to make them even, and I'll transfer the multiplier in front of the formula. So this 2 becomes 2 here. This multiplier goes up there as 3. This multiplier goes up there as 4. And this multiplier here. That's why the multiplier in the formula has to be the same. Goes up here as 3. And so now I have my equation balanced. Do you have to do it that way? No. If you like writing the numbers before like that, you can do that. Do whatever works for you. I'm just showing you a way to do it, and you can do it whatever way works for you. Okay, so 2, 3, 4, 3. Yeah, they start with the oxygens first and then move on and then move on. And then so many pages later, they got the answer. Okay, next question. Write a balanced equation for the combustion. Remember I told you about combustion, right? That thermodynamic term, that means burning. Combustion is burning. Now we haven't learned about types of reactions yet. We will. C4H10. Do they tell you what physical state that is in? It's gaseous. That means it's a gas. This is butane gas. Combustion is usually, in the combustion reaction, usually has some kind of fuel that is being burned in the presence of oxygen. So oxygen is a reactant that has to be present in combustion. So my first semester teaching as an adjunct, I'm fresh out of grad school. Well, not really super fresh, just like 1 year post grad school. I got a teaching gig on the side, my side job as an adjunct. And then we did an experiment with my students where we're supposed to be burning some fuel. It was some kind of organic fuel. They were supposed to use, I think, point zero 0.01 milliliter. It was supposed to be like one drop, but they used a whole dropper. They weren't reading directions well. And I was working with one group. Thank God they were in the fume hood. All I hear is fire. I turn around and I'm like, no. I mean, I appear calm on the outside, but on the inside, I'm like, no, this is my first gig. It's not gonna end like this. And so, per the training, okay, I was trained on how to deal with fires. It's in the safety video. I go grab the fire extinguisher, and as I'm heading towards the fire, an older gentleman who has more quote unquote life experience than I do, because the fire was happening inside the fume hood, he just pulls down the sash. Okay, so the fume hood has that glass shield that protects you from the chemicals in there. He had an experiential knowledge of combustion reaction that I didn't. Okay, to be honest with you, as a professional, I have to follow the rules, right? The rules say when you have a fire, use the fire extinguisher, not pull down the sash. He wasn't bound by those rules because he was a student. He pulled down the sash. And the thing with combustion reactions, if you run out of oxygen, you have no reaction. So of course, when he pulled down the sash, the oxygen amount ran out and the fire just stopped. And I'm standing there holding my fire extinguisher, like breathing hard, like, okay, thank you. And I went to put it back. I felt so stupid, but I was like, listen, I followed the rules, okay? If something had gone down and they came to me and asked me, did you follow the rules? My answer would have been yes. But sometimes the rules isn't the most practical way to deal with a situation, right? Combustion reaction require oxygen. Okay, so we have this butane here as your fuel, which they say here combines with gaseous oxygen. This is going to be a gas to form gaseous carbon dioxide, CO2. Remember nomenclature, naming compounds, you got to know that here, and gaseous water, H2O. This is also a gas. Oh, we're trying to balance this out, right? Like before. Carbon, 4. Hydrogen, 10. Oxygen, 2. Carbon, 1. Oxygen, 2. Hydrogen, 2. Oxygen, 1. Okay, so by quick examination, I see that I have 4 carbons on the left and 1 on the right, correct, as far as the amounts. Only one formula on the left has a carbon and one on the right has a carbon. One formula on the left has a hydrogen and one on the right has a hydrogen. One formula on the left has an oxygen, but 2 formulas have oxygens. If you have a scenario like that where it's more complicated, do the oxygen last. Try to balance the oxygen last because the oxygen appears in more than one formula. Okay? So I guess I'll try to balance the carbon. Start with that. I have 4 carbons on the left, multiply by 4 on the right to make the right one 4, multiply by 4, same compound to make this 8. Okay? And then let's see, I won't write anything before the formula, right? I only write the coefficient. That's what they're called. The number used to balance the equations are called coefficients. Coefficients. These are the multipliers that I use to balance the equations. I'm only going to write them after I know everything matches. Okay, so far the carbon's balanced. It looks like it. Hydrogen, let's see, times 5 to make 10, times 5 to make 5. Okay, the hydrogens look balanced. Now the oxygen, I deal with that last. Total oxygen on the left, 2. Total on the right, I have to add these two. 8 plus 5 is total oxygen, 13. Okay, compare the right oxygen to the left oxygen. I got 13 and I got 2 here on the left. Okay, so at this point, my high school kids taught me how they were taught. When this happens, go through and double everything. Okay, we can do it that way. Okay, which says that once you have a even and odd number situation with these oxygens, go through and double all the multipliers. Okay, so we take a step back and then we double these. So times 2 times 2, and then double everything else. So times 2, this becomes what? 8. Times 2, this becomes 20. Now you have to make the carbon 8. Okay, I'm trying to remove this because we're starting from scratch, kind of. I'm trying to make the carbon 8. So times 8 equal 8 times 8 equal what? 2 times 8, 16. I'm trying to make the hydrogen 20 times 10 equal 20 times 10, same formula, right? Equal 10. Okay, now I can recheck everything. Carbon is 8, carbon is 8. Hydrogen is 10, I'm sorry, hydrogen is 20, hydrogen is 20. Oxygen is 2, oxygen here is 16 plus 10, oxygen total 26. To make this 26, multiply by 13. Okay, so remember the 13 that was here, we have to multiply that by this number here to get 26. By doubling everything, essentially that's what we did, right? So now that everything is equal, I can go ahead and write the multipliers up there. So this 2 goes up here, the 13 goes up here, the 8 goes up here, the 10 goes up here, okay? And that's balanced. I don't have to double check it because, well, you can check it if you want, but I just made sure it was balanced down here. It's balanced up here, okay? So they work it out. They work it out. They use fractions. You can use fractions if you want, but in the end, they double everything and they end up with that. There's so many different methods of how to balance the equation, but that's what we get to. Okay, next one that we're working on is, oh, okay. Sorry, because the actual question is this part here, and I just copied the equation. This is the actual question. That one is just the work, right? So I need to write down the actual question, not the work they did trying to use shortcuts. Okay. Come on. Okay. I know why it's dragging. Okay. There. It's still holding on to that first one. What happened here? Hold on. Okay. Maybe I'm moving too fast. There. Delete. I'm trying to copy the actual question, but for some reason, it still has. Okay, hold on. Select. Wait for copy. Scoot over. Press. Paste. Okay. Finally, the right thing copied. Okay, in this problem here, it says write a balanced equation for the reaction between aqueous strontium chloride. So strontium chloride, because you want to know how to write the formula from the name. Strontium chloride, I look at my periodic table. Make sure you have a periodic table that has the names of the symbols, right? The elemental symbols. So strontium chloride, strontium is in group 2. So strontium chloride, this will be SR. In group 2, it will have a charge of 2 plus. Chloride in group 7 will have a charge of that. So this will be SrCl2 because you will crisscross them to make the compound. Okay? And they said aqueous, so this is going to be AQ. Next one is lithium phosphate. For lithium phosphate, so remember when we're naming this compound, okay, what I've done in my head behind the scenes is remember that this is a metal because I pulled out my periodic table and I have memorized what the metal is. So this is a metal, this is a non-metal. So this is an ionic compound. But not only is it a metal, it's a group A metal. So I'll say, let's say metal A. This is also a metal and it's from group A. So remember the name will just have two names, right? The element name and then the anion name. So from the template, I can tell what type of compound I'm dealing with. Here it says lithium phosphate. With lithium phosphate, I'm dealing with an A metal again because lithium is in the A is in 1A, right? This was in 2A. Phosphate is a anion, even though it's an oxyanion, but this is still a nonmetal. Okay. Lithium has the symbol Li, is positive because it's group 1. Phosphate has the symbol PO4 3 minus. If you've forgotten these symbols, go ahead and look at the list. The lab does have a list. So just in case, let me detour real quick because your lab this week has a list of polyatomic ions. I mean, the PowerPoint has it too. Wait, is this your class? Oh, this is the other. See, the other classes look very same. I'm like, why are we doing that all the way down? No, no, no. Oh my goodness. They posted all my summer classes. Now it's hard for me to get to anything. Making my list really long. Okay, here, let me go to the, where is it? This one here. Yeah, if you go to your lab, let me pull this out. Okay, this was scanned. This document was, oh, come on, document. Why won't it move? I feel like I'm struggling here. Okay, there it is. So yeah, they give you background on balancing equation, reactants, products, da da da. Oh, you know what? I'm looking at the wrong thing. This lab here has the balancing. I'm right about that part. But the part that has the naming is the naming compounds lab. Right. That's a different lab from the one I'm showing you. The naming compounds lab, I will strongly suggest the one that has ionic versus covalent compounds with this one here, that you take the, either you type it out because that will be helpful to you, but you want to have a list of polyatomic ions because that lab does have that list somewhere. Oh, there it is. You see, it has the sulfates, the hydrogen sulfates, all these right here. Either you type it out somewhere else and then you can post it or have it on your desk where you do your work so you can easily refer to all of these ions as needed, right? And then you have the ones that have the common variable charge metal ions. These are here too. You want to have these close to you, accessible to you, so you can pull them out. The more you use them, if you're not good at memorizing, the more you write out the formula yourself, the more you learn it. That's how I learned it. Back in my days, we didn't have Google the way y'all have Google, right? So we just worked on it until it stuck in the head. I wrote a lot of stuff down until it stuck. Okay, let me see. Where did I put my iPad screen? Oh, there it is. I know I have a lot of stuff going on here. Okay. Right. So this would be Li3PO4. And then it's telling you what it's going to form. It will form strontium phosphate. Strontium phosphate. Let me go a little faster on this part here. Phosphate will be Sr2 plus. Now they're switching partners. They're going along like that. PO4, 3, oops, 3 negative. 3 negative. So here, this comes down here, this comes down here. So the formula becomes strontium phosphate. You want to make sure you don't confuse the 4 and the 2 that came in after. And then these are all aqueous too, like as an also, and then you have lithium chloride. Okay, so I'm just doing the work right now to write down the formulas. Now these two are going together. So it's going to be LiCl, and this is aqueous. Oh, sorry. This is aqueous. I just realized when I read over, this is solid. Okay, so let's work this out. SrCl2 aqueous plus Li3PO4 aqueous gives you Sr3PO4 2 solid. Okay, I feel like I wrote too big. Let me shrink this a little bit. Plus LiCl aqueous. Okay, so let's try to balance this out. As usual, do a roll call. Sr, we have 1. Cl, we have 2. Li, we have 3. PO4, we have 1. So I'm going to look at PO4 because it's a polyatomic ion. I'm going to look at it as a group. And then here we have Sr3, PO4, 2. Now, if you want to look at each phosphate and each oxygen and list it that way, can you do that? Yes, you can. It will take you a little longer, but yes, you can. Oh, sorry, on the product side. I'm talking and writing and getting distracted. Li1, Cl1, right? So when I look at this, on the left I have 1 Sr, on the right I have 3 Srs. If I want to make the Srs equal, I can multiply the left one by 3, correct? Okay. Times 3 gives me 3, times 3 gives me 6. Okay. So right now it appears that the Srs are balanced. But in the process, I've changed the chlorines, and the chlorines are now 6. So times 6 to make 6 chlorines, times 6 same compound to make 6, right? Now it appears the chlorines are balanced. In the process, I changed the Li. Li on the right is 6. I have to make the left one 6 times 2 to make 6 times 2 to make 2. The Li's are balanced. Oh, look at that. The PO4 are balanced. Okay. Now I can take my multipliers and write them through, or write them in. This is going to be 6 on the right? The multiplier here is 6. The multiplier here is 2. The multiplier here is 3. And this should balance. So let's see what they say. Yep, they got 3. They do a lot of steps. Are we there yet? Oh, eventually. 3, 2, 1, 6. Right. Okay. We are finally at stoichiometry. So let's see. I'm trying to see if now I'll start before I do stoichiometry. Let me do a quick detour. We'll start stoichiometry next week. What I want to do right now, a quick detour to help you complete the lab. Even though we'll cover this towards the end, 'cause I'm looking at the time I have left, and I'm like, how much stoichiometry can I really do at this point? Not a whole lot. So let me do this. Before I get into stoichiometry, let me do a detour. Oh, I'm like, where is my... Never actually used that page before. Okay. So I want to detour here. So I'm going to add a couple of pages. And so since I saw your lab, this is to help you finish your lab on time. Okay. So to complete, or actually, let me keep it simple. Instead of completing reaction, because I'm looking at the time I have left, I'm like, I don't have enough time to complete the reaction. I'm just going to focus on identify types of reactions. Yeah, I don't have time to go over completing the reactions, okay? I just focus on identifying types of reactions. But in the process, I'm kind of going over completing the reaction. The most common top 5 types of reactions that we cover are the following. We cover synthesis or combination. Okay, let me give myself some room. Synthesis or combination. This is the kind of reaction where you identify a synthesis. So this is what we notice, right? I'll call this the identifier. Okay, this is this is not a very good term. How about characteristics? Characteristics. Okay. The characteristics that we see in this chemical reaction is usually that it forms one type of product, not one amount, just one type. Okay, so you have many reactants that form one type of product. So that's why they're called combination. It's like combining many pieces to make a whole. Okay, so the synthesis reaction, synthesis or combination, you have many types combining to form one type. So let me see here. Somewhere here we do have that lab that I opened, right? That wasn't it. Okay, let's go back here. I'm going to use your lab as a example for this. So somewhere here in this long dialogue, right, they use the term synthesis right here. Oops, I highlighted the whole thing. But you see where the mouse is, synthesis, category, synthesis, decomposition, single, replacement, double, replacement, combustion. And they give you the example here is X plus Y to give you Z. Okay, so here you can say you have X plus Y compounds and they combine to form Z. Now it can form many Z's, but only one type of product. Okay, and then you have here many reactants. Now the reactants can be elements, they can be compounds. Yeah, it can be elements or compounds. Just many reactants, one type of product. So let's go ahead and look at this example here. I won't highlight all of them. How about we do the first couple of pages? Let's see if we can find the, so here's where I want you to come in and say something. Wait, how do I not cancel this out? Minimize this. So I want to see what you're saying. So for this one here, this is just showing you how to read the number of atoms here, right? Okay. Oh, they gave you the first one. This first reaction type is synthesis. By the way, for this lab, you don't have to do the molecular representation if you don't want to. It's tedious. You can do it if you want to. It won't add any more points or less points. You can just go straight to balancing the equation. The molecular representation helps you to balance the equation, but I showed you a different way of balancing the equation, so that part is unnecessary. So I'll just cover page number, this is 4, right? 5 and 6. So on page 5, we found our first synthesis reaction, right? Element, element, compound. These two are classified as elements, diatomic elements, but elements, right? It's just H twice, O twice, and then H2O compound. Okay. So let's see. Which number here in this page would you say is another synthesis? Hold on. Ah, can you see another synthesis reaction here on this page? Of the remaining reactions where you have maybe elements combining to form compounds? So let me write here. The other way of seeing it is you're going to have element and element to form compound. Okay. So if you're saying you're not sure, then I guess we have to make sure we know what an element is, right? So elements tend to just be one element symbol. I don't. I just realized I'm using the word to define the word. This is not very helpful. Okay. So can I write here? I can't write much here. Let me write on the. Let me tell you why this first one here is synthesis, right? Hold on. Okay. In the first one, which I've already forgotten what it was, we were making water. Okay. We had H2 adding to O2 to give you H2O. This is an element. This is also an element. And this right here is a compound. What makes this a compound? You have two or more elements combined, right? Combined. You see we have a hydrogen and then we have oxygen in the formula. Okay. Here, yeah, we have two elements, but it's two, oh, sorry, I should add here, two or more different elements, not just two or more elements, two or more different elements combined. Okay. So two or more different elements combined. The hydrogen and the oxygen are different elements. Over here, we have, though we have two elements combined, they're two of the same element. So this is still classified as element because you have two of the same elements combined, but it has that special name, diatomic. That means two of that element. Same thing with this one here. You have hydrogen and hydrogen combined, right? Because they're the same. This is also called diatomic element. So when you have an element combined with an element to make a compound, that is classified as combination or synthesis. Okay? Even if the element is just monoatomic. So let me show you. Number one is definitely synthesis of combination. Number two is not, because you can see how we have two different elements here. Lead is, one, and then Cl is another one. So there's too much going on here for any of these to be an element, right? Look at 3. This is an element. Silicon is monoatomic because it only has one symbol, silicon, Si, right? So you want to make sure you're familiar with the symbols for the element too. So this is an element. This is an element. On the right, they make one formula, one type of formula, right? They combine with each other to make a compound. So this will also be a synthesis reaction or combination. Okay, does that help? This one here, ClCl, this is still an element. KNBr, this is classified as a compound. So this doesn't apply to our situation. We're trying to get things that are pretty much elements. So for number 3 here, as we're working on this, Si plus Cl2 to produce SiCl4. And then number 5 is also synthesis NaCl2 to give us NaCl. These are all synthesis. So as I said, oh no, why do I keep doing this? Let me see. Is the page open somewhere here? Yeah, the page is in the bottom. Right. This is an element, monoatomic, because it's only one. Monoatomic. This is 2 Cls, right? This is just one Si, 2 Cls. Still an element, but diatomic. This was a Si combined with a Cl, combined with a Cl, combined with a Cl, combined with a Cl. This is definitely a compound because different elements are combined together. So this is a compound. That's it, compound. Okay? So when we're classifying these types of reactions, As long as we have elements combining to form compound on the right side, that is classified as synthesis. Same thing here, element, element, compound. Okay, so we got synthesis here, synthesis here, synthesis here. Okay, so I'm going to move on and talk about the reverse of synthesis, which is type number 2, which is decomposition. In decomposition reaction, you pretty much take what you understand about synthesis and then reverse it, flip it over. In decomposition, you're having a breakdown. So I remember one class I had pre-nursing students. That was the first time we started having the state had changed the prerequisites for chemistry, requiring pre-nursing students to take general chemistry. So for the first time, I'm seeing them in my class. I'm like, okay, can you guys give me an example of decomposition? They said, yeah, dead bodies decomposing. I was like, wow, dead body. That's deep. I mean, yeah, it's true. Dead bodies do decompose, but I was expecting a chemical reaction example. So I had to think differently, like, okay, I need to be more specific in my question because I do have a slightly different audience than what I'm used to right now. So all we can do here is flip these. Let's go through and flip these. Sodium chloride, right? Decomposing to form sodium and chlorine. Just flip the first equation. Water decomposing to form water molecule and oxygen. We talked about this before, but I want to bring it up again. When we look at these here, why do I write these as 2 and this as 2 when it's by itself and then sodium as 1? Remember, we learned this before. It was a list of elements called Brinkelhoff, which my students taught me this. Brinkelhoff, when you have bromine, iodine, nitrogen, chlorine, hydrogen, oxygen, and fluorine. When these elements are by themselves, they exist as diatomic. So only these are diatomic. That means when you see them by themselves, they will always have a 2 below them like that. 2, a 2, a 2, a 2, and a 2. So you see chlorine, this one here has a 2. Oxygen has a 2. Hydrogen has a 2. If we have fluorine somewhere in here, they'll have a 2 because they're part of that Brinkelhoff family. Okay. And then what else do we have here? Water. Oh, SiCl4. Break this down. Si. Since Cl is part of the Brinkelhoff, Cl2. Okay. And of course, you want to balance it out. So you have put 2 here. Put 2 here, this balances it out. You want to balance this out, you put 2 here, balances it out. To put 2 here, and this balances out. Okay, so these are all examples of decomposition. So how do you describe this to someone? In decomposition reaction, you have one type of reactant breaking down to form many products. So you have one forming many, okay? Okay, the reverse of synthesis. Then number 3, we have single displacement. In single displacement reaction, oh, I gave you a format earlier, right? Let me highlight. This is the format. Element plus element to give you compound, right? Like a template. Element plus element gives you compound. Here, I should say compound breaks down to element plus element. Sometimes it can also give you a compound, but I'll say if it does give you a compound, it's always a smaller compound. So that's kind of the template, right? Compound breaks down to give you element and element, and if it does give you a compound, it gives you a small compound. Okay, single displacement. What you're looking for in single displacement is this format here. Compound plus element to give you compound plus element. In single displacement, what we see here is element displacing. Oh, that word won't make it there. another element in a compound. Okay? So when you're looking for a single displacement reaction, this is the one that I say kind of has a sad story. Okay? Let me give you an example. Compound. Let me say HCl plus element sodium. Okay? So you can see HCl here. And in this situation here, so this is my example. Hydrogen is the first element, so it's positive ionic compound, and then chlorine is negative. When sodium forms an ion, it's positive. So when I'm writing out my product, the positive can replace the positive, and that's it. The positive cannot replace the negative. Okay? So remember, single displacement. Now, this is what happens. Sodium displaces or replaces hydrogen in the compound. Hydrogen thought he had it good when he was with chlorine, but someone better came along. And chlorine has a preference for sodium than hydrogen. Chlorine will remain with hydrogen as long as sodium is not around, right? This sounds like a tabloids that they sell at Walmart. They were in love, and then sodium came around. And then when sodium came around, it's like chlorine never even knew hydrogen at all. Sodium replaced hydrogen so quickly. Now hydrogen found itself alone. But remember, hydrogen is part of that Brinkelhoff family. Brinkelhoff right here. So when it's by itself, it always exists as diatomic. So there, single displacement. So for this, you have to double this to balance, 2 right there, then double that, then you double this. But bottom line here is, this is an example of single displacement because you have a compound, right, made up of hydrogen and chlorine. You have element made up of sodium. You have compound made up of sodium and chlorine. And then here you have an element, diatomic, made up of 2 hydrogens, right? So compound element. So when you have that compound, I mean that format, CC, compound element, it may be written, in a different order, but you have that combination, then you know that you have single displacement. Okay, number 4. What about double displacement? Double displacement. In double displacement, what we see here is compound plus compound to give you compound plus compound. Okay? So you see 4 compounds. With this one here, for us to have a chemical reaction, what we observe is they switch partners. Partners. Okay? So it's like one of those line dance. I actually got a chance to line dance one time in Mesquite. It was like a country line dance. So I'm like, yeah. And the guy was calling the move. Da, da, da. I have no idea what's going on. I'm just copying everybody. We're just screaming, yay. It was like a teacher conference thing. Then we never switched partners. I'm like, what is this? My whole life, well, not my whole life, I've thought about switching partners in the line dance. We never got that chance. We never did that whole switch partner. Okay. Let me give you an example of this. Compound, sodium hydroxide. Another compound, HCl. Okay, so I know these are compounds because there are many elements that are different, right? Let's see how they switch partners when they switch. Sodium, which is positive, the hydroxide is negative, hydrogen is positive, chlorine is negative. Sodium goes off with chlorine, then hydrogen goes off with OH. So sodium goes off with chlorine, and then hydrogen goes off with OH. So HOH essentially is H2O. Okay? So this is sodium hydroxide plus hydrogen chloride or hydrochloric acid to give a sodium chloride plus water. Okay? Compound, 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 compound. Then my last one, and I'll let you go. You can work on your, at least most of your lab. This is going to be combustion. We talked about combustion before, but we're talking about it again. In the combustion reaction, you have this format, a compound, an element to give you a compound, and a compound. The first compound is a fuel. The second element, the element is oxygen. And then this compound here is an oxide. And then this other one here is an oxide. Okay? Or should I say water? Water. So let me give you an actual example based on something that we already covered. Here, let's say we have CH4. The fuel tends to have this format. So let me kind of show you how the CXHY. It can have other formulas similar to that, but it has that format in the formula. So like CH4. The X and the Y could be different numbers, right? So you see how it's similar to that format? And then plus oxygen. That matches that, that matches that. The oxide here is just carbon dioxide plus water. We all know what water looks like, H2O. So when you see a chemical reaction that has this format, a compound and an element, a compound and a compound, where the second compound is water, the element is oxygen, then you can conclude this is a combustion reaction. Okay, so combustion. Let me see. I said I was going to look at your first 2 pages of your lab, right? So let's go back to your lab. Can I write here? Maybe with a highlighter. Ooh, okay, good. Let's see. I hope it doesn't save on y'all's end. Yeah, this is definitely an element. Oh, this wasn't meant for writing, but you can see H2 element. Oh, it won't let me. Oh, so I need to write like this: element, element, compound. So this is going to be synthesis. These are 2 different elements. So this is going to be compound. 3 different elements. Remember, minimum is 2 and up. Compound. 3 different elements, compound. 2 different elements, compound. When you have compound, compound forming compound, compound, double displacement, right? I have to write it in such a way that they will allow me to write. Okay, double displacement. Okay, this is element, element, compound, right? So EEC, synthesis. I'll just write it as synth for synthesis. EEC again, you see the format, right? Synthesis. So I'm trying to make this as mathematical as I can, as possible, because that's where my strength is. My strength is not in words. My strength of understanding is in numbers. So if I see that logical sequence, not logical, but that sequence of EEC, element, element, compound, I can recognize the synthesis. Element, element, compound, synthesis. Compound, 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 double displacement. So I'm kind of going by that, right? Let's see here. Element, compound, compound. Oh, I knew it. They won't allow me to write like that. So E, C, C, E. I told you before, when you have C and E on the left and C and E on the right, then you have single displacement, versus when all 4 are C's, you have double displacement. Okay. So here, what is this? E, E, C. Oh, I did this before. Like that. Synthesis. I like to work problems from scratch each time because, oh, come on, they let me write it here. Okay. It won't. Man. Okay. Synthesis. This is okay. I said I was gonna work on. What about this one? You know what? I'm hard of learning to do that. Element, compound. EE, synthesis. Okay, you get. Okay. And then this one here, elements. Many elements also, but this is smaller than that, right? So compound, compound, compound. Ooh, okay, hold on a second. But look, even though we have 4 C's, there's only 1 C. Okay, I didn't make that in time. There's only one huge compound on the left and everything on the right is smaller. What do you think that one is? There's only one compound on the left. So you have one making many small ones. I know it's slightly different. Yes, decomposition. Even though I don't see the full word here, but I'm just making an assumption. What did I do? Oh no. Okay. Yes, decomposition. Because you have a big formula on the left breaking down to small ones. Right. The formula thing is not 100%, but you get the idea. When you have one formula on the left and then many on the right, that's decomposition. Right. Okay, here, let's see. This is where the arrow is. We have many on the left and then one on the right. We have element, element, compound. What do you think number 8 is? Synthesis. Yeah. Number 9. We got compound, we got element, we got compound, we got compound. And then, so it's CECC. And then the element is oxygen. The compound is water. So we have CECC, then the element is oxygen, and then the second compound is water. Which one does that one match? So you want to look at your list. Combustion, yeah. See? So that's how I survive this because I have to find a way to help myself with this part, right? And then let's see, zinc by itself, element, uh, compound, compound, element, right? One of each on the left, one of each. Element, compound, compound, element. What do you think number 10 is? Single displacement. Yeah, exactly. So see, not that bad. So I mean, as I showed you, at some point when I was teaching this, I'll try to show every combination, and the students were overwhelmed. And I figured, okay, let me give you a little bit. As you work on it, you will see the variations, right? Because the thing with chemistry, it's a problem-solving class. So you may learn something one way, and then you see it differently, but they want you to be adaptable in your problem-solving journey, right? So if you learn it one way and you see it differently, you want to be able to kind of transition into the new way of learning it. So yeah, that's it. You can work on the rest of these. I believe you can do it. The remaining 10. And then of course you have, I think I told you how many of these to work on. Then you can work on the rest of these. But same idea. Go through and then write the type. And of course this will also help you to know how to identify elements in the compounds, right? And you can tell which is which. You can tell the different types of reaction. So we'll pick this up on Monday next week. Yeah. But this is all I have for today. Oh, I forgot. I have my other class coming up. I'm sorry. It's a new class that started a couple of weeks ago. So that's why I have, you see, that's why I have things in calendar. Because I'm like, what is that? I put it in my calendar so I don't forget. Oh my goodness. Yeah, teachers are forgetful too. I know I'm forgetful. Yeah, my other class is coming up in 15 minutes. Cancel. Hold on. Okay.